Hi, my name is Dario Schulz, and in this video I will speak about a spatially explicit analysis of agricultural innovation adoption determinants. Sustainable intensification of agriculture is considered crucial to reconcile the increasing demand for food, feed and fibers with the long-term integrity of the ecosystems that are often degraded. Many existing agricultural innovations improve resource use efficiency, which is the ability to produce the same output with less input, or help to mitigate and adapt to risks arising from external pressures, such as climate change, in ways that support and enhance the provision of ecosystem services. Whether or not a farmer decides to make use of an available innovation depends on a variety of factors that are not always well understood. A large number of cross-sectional analysis has been published looking at many of such determinants of adoption, or its intensity, but always for a specific population and a selected subset of agricultural innovations. A couple of reviews have tried to synthesize the results of these studies, but always with a regional focus and/or a subset of agricultural innovations. The objective of this study is therefore to provide a globally representative meta-analysis of available evidence considering a wide set of agricultural technologies and practices. Understanding the drivers of technology adoption in the past can help us to find relevant patterns which shape the adoption of future technologies that may not yet exist. The research question this meta-analysis tries to answer are: first, what are globally consistent farm-level determinants of innovation adoption and what is the magnitude? Second, can geographic context explain the variance in the magnitude of adoption determinants? In this context, I want to test the induced innovation hypothesis, or whether technological change is driven by relative factor scarcities in a given geographic context. The data collection and coding is an ongoing team effort, and I would like to acknowledge the effort and thank my colleague Philipp Feistauer and our research assistants in particular. After identifying about 1,300 potentially relevant studies from prior reviews, we retrieved a substantial amount of primary studies from a database query that we filtered by journal quality before conducting an eligibility assessment. To be eligible, a study must report the results of an ex post multiple regression analysis of crop farmers adopting a new practice, technology or innovation on farm level and a control group of non-adopters. Since the number of studies is still very large, the preliminary results presented here are based on the subset of studies that estimate determinants of discrete adoption outcomes using logit or probit models. Each estimated regression coefficient from the primary studies is then coded according to over 60 variables, generating an exhaustive set of control variables for the meta-analysis. Of course, this depends largely on the amount and quality of data provided in the primary studies, and not all effects are comparable. Here's what the data structure looks like. Currently, there are more than 12,000 observations belonging to more than 50 categories of adoption drivers. But only some of these categories can be analyzed because they should be comparable and contain a minimum number of observations for robustness. In addition to information such as scale, unit, summary statistics of the sample, or precision of the estimate, this study adds secondary data to each observation to analyze the role of spatial context. Context relates to the production system characteristics, agri-ecological and socio-political context. And this analysis will particularly consider the main production factors: land, labor, capital, and know-how. The spatial location of each primary study is used to extract the relevant context information from secondary data sources. At this stage, the analysis only includes secondary data from the World Bank and the Food and Agricultural Organization, which is available at country level. But for a subset of regional studies, I will try to exploit within-country heterogeneity from different maps. So how can we aggregate the results from many adoption studies? The dependent variable in the meta-analysis regression are estimated beta coefficients of one specific adoption determinant, for example, years of formal education. I use their log odds ratios as a comparable effect size. Each effect size T from study I is an estimate of the true sample-specific effect, here denoted by theta, from which it differs by a random sampling error epsilon. Since we cannot assume that the true effect is equal among all studies, I use a random effects meta-regression model and estimate the mean and variance of the distribution of the true effect sizes. All feeders constitute the distribution of the overall effect mu. I call the study-specific error term of mu u1 and its variance tau. In the simple random effects model, each observation receives a weight based on the within and between study variance. But then, each primary study can include multiple effect estimates from the same sample, for example when it estimates adoption of more than one technology or employs more than one model specification. So to account for stochastically dependent effects and potential homoscedasticity within study clusters, I use a covariance matrix for the calculation of single observation weights. Furthermore, I use a multi-level model structure with fixed effects at the study level and agroecological zone level because the drivers of technology adoption, such as climate change, risk exposure, are likely to differ among fundamentally different production contexts. In the basic effect aggregation model, the magnitudes of the adoption determinants are estimated by the overall intercept and its robust confidence intervals, which are clustered at the study level. In the second step, a set of moderators that vary on study and zonal level is included to explain the variance of the true effects. I include different sets of moderators and sequentially add control variables for study characteristics. All meta-regressions include dummy variables for the observation level and effect units. Additional sets of moderators are then included to check for robustness of the context variables by controlling for model specifications. More interesting are then the innovation trait dummies that were coded according to a theory-informed scheme. The inclusion of these traits allows to control for innovation characteristics like risk reduction or path dependency. So far, there are 3 sets of context variables, all of them at the country level. They include an indicator of governance quality, land and labor productivity, and, as a proxy of education, the share of a country's workforce with primary, secondary, and tertiary education. The size of the circles in this map indicates the number of analyses available per country, and the color of the pieces indicate the respective innovation category. Clearly, the United States are overrepresented, while Latin America, Europe, and Asia are lacking observations. This has to do with a language bias. We searched only English journals, and we are trying to reduce this bias systematically by purposely including more studies from underrepresented regions. Depending on the effects of interest, there are different numbers of observations, because some variables, such as farm size, are included more frequently in adoption studies than others. So now we look at some preliminary results. This plot shows the aggregated estimate of adoption determinants by innovation category. The bold estimate at the bottom of each driver is the overall effect size. We can see that affiliation to farmer groups, access to assistance and credit, education and farm size have positive effect estimates, and their robust confidence intervals do not include 0. All other effect estimates that were included so far, for example whether a farmer owns his or her land, are very close to 0, but the number of observations is also much smaller. Looking at effects group-wise allows to study potential moderators. For example, the overall effect of a larger farm size is positive and the 95% confidence interval does not include 0. But there are multiple estimates below 0, particularly in the innovation categories of fertilizer use, intensity optimization, and conservation. This indicates that the variance in the beta estimates of farm size depend on the innovation, which makes intuitively a lot of sense and can later be controlled for in the regression. Assistance B, where the B stands for the subset of binary measures and C for the continuous measures, has a larger positive effect, but also more variation in it. Similarly, when education is measured on a continuous scale like the number of years, its positive effect is small and has a small variance. When it is measured as a dummy, the effect is larger and more uncertain. That is because dummies like graduated from college or is literate are very different and the measurement unit has to be controlled for. In the last slides, I will now present some selected highlights from the context analysis. We now turn to the beta coefficients of years of formal education as the dependent variable. I found that the effect is positively influenced by the length of compulsory education in a country. This moderating effect is small, but remains stable for all model specifications shown on the left side, and we have to remember that the total variance in the beta estimates was also quite small. This plot indicates that more years of formal education are more important for adoption in contexts where the compulsory number of years of education is higher. In addition, I found a hint that the betas are also larger in contexts where labor productivity is higher. Turning to the beta coefficients of farm size as the dependent variable, results suggest that in contexts with high labor productivity, farm size is less of an adoption determinant. However, that effect was not robust to the inclusion of innovation traits. When innovation require capital, farm size is more important, but farm size is a less important determinant for the adoption of risk-reducing innovations. When looking at capital, specifically the betas of those binary variables describing access to and use of formal credit, the importance to include variables that describe model specifications becomes clearly visible. Without the inclusion of model specification dummies, the estimated effect of land and labor productivity is opposite to the estimate where these dummies are included. What we can see is that capital access is a weaker driver of innovation adoption in context of high land productivity, but a stronger driver in context of high labor productivity. The driving force of assistant behaves very similar to credit access, although much stronger in magnitude. It also increases with labor productivity and decreases with land productivity. It is not shown here, but another interesting result from these regressions was that assistance seems to become less important with an increasingly educated workforce. What does it imply that one additional year of education is more important driver when its average levels are higher? A possible explanation could be that formal education is less about the skill level and more about the ability to acquire and make use of new information. The larger effect represents the returns to human capital formation. Also, it is more relevant for land-intensive, productivity-increasing innovations where impacts are hard to observe, which is rather intuitive. I will not further discuss the farm size effect here because the identified effects were not robust. The effect of access to formal credit increases with labor productivity. In contexts of low labor productivity, payment may be informal and not require credit. Furthermore, for a credit to be useful, the obtained labor productivity gains have to be high enough to justify the cost of a loan. This may not be the case when labor productivity is low. Furthermore, it decreases with land productivity, likely because in such contexts, where land is already productive, capital may be less of a constraint for technology adoption because land is the rather scarce factor. Finally, the assistance effect decreases with land productivity. One would expect that where land productivity is high, assistance can only provide little additional information and its effect on the adoption decision is rather marginal. On the other hand, land productivity may be low because assistance is not available, and once it becomes available, it will trigger innovation adoption much stronger. Hence, this relation seems to be endogenous, but provides a nice way to test the overall analysis assumptions and data validity. To wrap it up, here is an overview of the effects that have been analyzed so far. Access to assistance has the strongest effect, particularly in contexts of low land productivity. This highlights the importance of extension systems for agricultural transformation. Farm size, education, and access to credit are positively associated with innovation adoption, and some context moderators seem to explain a significant amount of their variation across space. Other drivers and barriers of adoption, like market distance or ownership, have not yet been analyzed. For the future, the primary goal is to increase representativeness and external validity by increasing the sample size across all countries and look at other adoption determinants like network effects. The primary studies use logit and probit models, and all their effects are subject to a scaling factor, so we have to pay special attention to the model control dummies and will perform sensitivity analysis. Hopefully, we get enough study samples to run meta-regressions on a subnational level. Another point of interest, especially for innovation designers and policymakers, could be the interaction of innovation traits and context variables, so this could be an interesting topic to look at. With that, I would like to thank you for your attention and look forward to getting your questions and feedback.
Thank you for your attention.